Hello ma'am. My first question is that how the throttling process is taking place in cogeneration system. Second question is that please solve one problem when the throttling process is taking place in cogeneration system with the help of the Mollier diagram and steam table. Let us understand throttling process in cogeneration system with the help of diagram. In boiler, high pressure and high temperature steam is getting generated and it is passed through this throttling process. Now what is this throttling process? So it is the partial reduction of the pressure with constant enthalpy. So when this steam is passing through this throttling process, then from this point 1 to 1 dash, enthalpy remains same, but the pressure of steam is getting reduced. Now this reduced pressure steam is passed through to the turbine where the isentropic expansion process is taking place. That means entropy remains constant and here is the expansion of the steam and the mechanical energy is getting converted into electrical energy in this generator and power is getting developed. Now at the exit point of turbine there is the mixture of steam and water. And this mixture is passed through the process plant where the heat is supplied and the whole mixture, that is steam and water, is getting converted into saturated water. And this saturated water is again pumped to the boiler. Now we will solve one problem to understand how to use the psychrometric chart when the throttling process is taking place. I will read what is the given question. Steam at 15 bar and 250 degrees Celsius is supplied to a back pressure turbine whose exhaust pressure is 1.5 bar and its isentropic efficiency is 80%. The net electrical power developed is 500 kilowatt. The mechanical efficiency of the system is 90% and generator efficiency is 95%. If the condensate coming out from the process plant is fed back to the boiler, find out the steam supplied to the system in kilogram per hour, heat used in the process plant in megajoule per hour. If the steam supply pressure is reduced to 50% by throttling to take the new reduced load to 50% of original, then find out the steam supply to the system and heat available for the process plant. Assume all other conditions are same as 100% load. So this was the given question. Let us first understand the given data with the help of diagram. Steam supplied to the turbine, it is given that for 15 bar and 250 degrees Celsius. So here is the entrance point of the turbine and the steam we have to show at 15 bar and 250 degrees Celsius. Then the exhaust pressure is 1 bar. So in turbine isentropic expansion process is taking place and the pressure is getting reduced. So we will say that the exit point here pressure is equal to 1 bar. Now isentropic efficiency is given, that is 80%. So isentropic expansion is taking place in turbine. So isentropic efficiency theta I is equal to 80%. Now we will understand how to use this term to find out the enthalpy at point 2. Now we will consider at the entrance point of the turbine, here will be the point 1, that is the condition of steam, and at the exit point of the turbine we will say that the condition of steam will be at point 2. Now if I show here the enthalpy entropy diagram, that is suppose this is the H and S, that is the enthalpy entropy diagram, and here is the point 1, that is the condition of steam before entering to the turbine. Then isentropic expansion process is taking place, that means entropy remains constant. So we have to draw here one straight vertical line. So this is the point 2 at a pressure of 1 bar. So here we will say that this is the point 1 and this is the point 2 dash, because the isentropic process is taking place. Now we have to consider this isentropic efficiency 80%. So how we can say that? We have to take this difference, that is the enthalpy at point 1 and enthalpy at point 2 dash, and we have to multiply this with 80% efficiency. Then we will get the actual difference in between enthalpy at point 1 and enthalpy at point 2. So for this I will write, that is isentropic efficiency and this isentropic expansion process. Here is the enthalpy H1 and here is the enthalpy H2 dash. So we will take the difference, that is H1 minus H2 dash multiplied by, we have to take efficiency, that is 80%. So we will write here 0.80 is equal to, now actual enthalpy is H2, so we have to take, which is equal to H1 minus H2. So remember, this is the important formula because here the isentropic efficiency is given. So turbine efficiency is not given, but isentropic efficiency is given. So we have to use this formula to calculate the H2. Now we will move for the next. Now here electrical power developed is given 500 kilowatt. Now we know that in generator electrical power is developed. So we will show that here from the generator power developed is 500 kilowatt. Now mechanical efficiency of the system is 90%. Now we know that in turbine mechanical energy is getting converted into electrical energy, and in generator here the power is getting developed. So mechanical efficiency is given neta m 90%. So I will write here, that is neta m is equal to 90%. Then generator efficiency is 95%. So in generator, when the electrical energy or when the power is getting developed, then here generator efficiency is 95%. So we will say that neta G is equal to 95%. Now we will move to the next. So here the steam pressure at 1 bar, here the steam as well as water mixture is entering into the process plant and heat is supplied to the process plant. So when it is coming out to the process plant, then it is in the condition of saturated water. So here the enthalpy is the saturated water. So we will say that here at the exit point of the process plant we have to find out the enthalpy HF2. Why suffix F is there? Because the fluid is in the form of liquid, that is the saturated water. So we have to find out the enthalpy of liquid at point 2 and pressure remains same. So here H2, enthalpy H2 is there, and at the exit point here enthalpy HF2 is there. And again the saturated water is pumped back to the boiler. Now for this given data we have to find out what is the steam supplied, that is the amount of steam supplied to the process, that is MS we have to find out, and we have to find out the heat supplied to the process plant. We will solve the first part of the question, that is the cogeneration system without throttling. Let us first understand what is the relation in between the power developed by the turbine and power developed by the generator. So in turbine there are the mechanical parts which convert the mechanical energy into electrical energy, and this generator here is the electrical power is getting developed. Now efficiency of this mechanical energy is given 90% and generator efficiency is 95% is given. So we have to consider these both efficiencies when we take the relation in between this power developed by turbine and power developed by the generator. So we can say that the power developed by the generator is equal to mechanical efficiency multiplied by the generator efficiency multiplied by the power developed by the turbine. So we will use here, that is Pg is equal to neta m neta g into Pt. So here all the values are known except power developed by the turbine. So we will put all the values. Here power developed by generator is given 500 kilowatt. Therefore Pt is equal to 584.8 kilowatt. So this is the power developed by the turbine. Now we will find out what is the value of HF2 with the help of the steam table. Now we know that here the pressure will remain same throughout this process plant, that is 1.5 bar. So at 1.5 bar pressure, what is the value of HF2? So here we will use the pressure table, that is saturated water and steam. Inside bracket there is pressure, and in the first column pressure is given. So we have to find out 1.5 bar pressure, and here is 1.5 bar, and we will find out the value of HF, that is 467 kilojoule per kilogram. Now when the isentropic process is taking place in the turbine, then we have to find out the value of H1, that is at point 1 at 15 bar and 250 degrees Celsius, and with entropy remains constant, we have to find out the value of H2 dash at 1.5 bar. This is the Mollier diagram and also known as enthalpy entropy diagram. So here is the enthalpy on vertical line and entropy on horizontal line. Now we will select the point 1 and point 2 as per the given conditions. So if we observe initial condition 15 bar and 250 degrees Celsius, so we will select here the point 1. Here is 10 bar, 20 bar. So in between this 10 and 20, here is the pressure line is for 15 bar, and temperature is given 250 degrees Celsius. So we will enlarge this diagram. So temperature is 250 degrees Celsius. So if we observe, here is the line with 250 degrees Celsius, and here is the point of intersection. So this point will be point 1. Now how to find out the enthalpy at this point? So we will take here one line and passing through this point. So we will draw here one horizontal line. Now if we observe, this line is below this 3000, so we will take here the exact value, that is 2930 kilojoule per kilogram. Now we will move for the point 2. So how to draw here the point 2? So in turbine, isentropic expansion process is taking place. So we have to draw here straight vertical line. And for final condition, it is given the pressure up to this 1.5 bar. So again, if we observe here, the pressure is given, that is 0.5 bar, 1 bar. So in between this 1 and 2, there is the pressure line for the 1.5 bar. So we will draw here one straight vertical line passing through this point 1. So I will draw here straight vertical line. And now we have to draw this line up to the pressure of 1.5 bar. So if we observe here, after this 1 bar, this is the line that we have to select. And after that, in between this 1 and 2, this is the pressure line for the 1.5 bar. So this point will be point 2 dash. Now for this point 2 dash, how to find out the enthalpy? So again, we will take here one line passing through this point, and we will measure the enthalpy. So enthalpy is 2500 kilojoule per kilogram. Now here, how to find out the exact enthalpy at this point 2, because this is the process, that is the isentropic expansion process, and isentropic efficiency is 0.8. So there is the formula H1 minus H2 dash into 0.8, which is equal to H1 minus H2. Now here the value of H1 and H2 dash are known, and only one unknown value, that is H2. So value of H2, or answer of H2, is 2586 kilojoule per kilogram. Now we know that the power developed by the turbine. So power developed by the turbine is given by PT. Now if we observe this diagram, how we will find out the power developed by the turbine? So it is equal to steam supplied to the system multiplied by the enthalpy difference. So enthalpy difference is in between this H1 and H2. So we will say that Pt is equal to ms h1 minus h2. So we will put the value. So here only one unknown value, that is the mass of steam supplied to the system, that is ms. So ms is equal to 1.7 kilogram per second. But the question is that we have to find out in kilogram per hour. That is, this is the amount of steam supplied in 1 second. So in 1 hour, how much amount of steam supplied? So in 1 hour there are total 3600 seconds. So we have to multiply this with 3600. Then we will get the answer 1.7 into 3600 kilogram per hour. This is the answer of first question. Now we will move for the second question, that is the heat supplied to the process plant. So again, heat supplied to the process plant is the amount of mass of steam supplied multiplied by the enthalpy difference. Now if we observe this diagram, enthalpy difference is before entering to the process plant, steam is having enthalpy H2 and after that it is having enthalpy HF2. So we have to take the difference in between H2 and HF2. So we will take ms H2 minus HF2. Now this ms mass of steam supplied we will take in kilogram per hour. So this kilogram per hour, that is 6120 multiplied by 2586 minus 467. So it is 12.97 into 10 raised to 6 kilojoule per hour. But in question it is mentioned that we have to find out in megajoule per hour. So we have to divide it by 10 raised to 3. Then we will get 12.96 into 10 raised to 3 megajoule per hour. And this is the answer of second question. Now we will move to the second part of the question, that is when the throttling process is taking place. So we will understand the given data with the help of the diagram. Now the initial condition of steam is at 15 bar and 250 degrees Celsius. Now here the 50% the pressure is getting reduced to reduce the load of 50% with the help of the throttling process. That means we can say that 50% pressure is getting reduced in the throttling process. Here the initial pressure is 15 bar. So we have to take the after the throttling process 50% reduction in this pressure. That means 15 divided by 2. So we can say that here 7.5 bar pressure of the steam is there after the throttling process. Now we will consider the initial condition of steam is at point 1 and after throttling process this condition of steam is at point 1 dash. Now what is the throttling process? The pressure is getting reduced but the enthalpy will remain same. Now we will understand this process with the help of this enthalpy entropy diagram. So we will select the point 1 for the 15 bar pressure and 250 degrees Celsius. So suppose here is the temperature of 250 degrees Celsius. Then here is the point 1. Now when the throttling process is taking place, enthalpy will remain same but the pressure is getting reduced up to the 7.5 bar. So how to select this point 1 dash? So enthalpy will remain same, that is this is the enthalpy, that is H1 at this point 1. Now this H1 will remain same and here is the 7.5 bar pressure line. So we have to extend this horizontal line and here will be the point 1 dash. Now this point 1 dash is the condition of steam before entering to the turbine. Now in turbine isentropic expansion process is taking place, that means entropy remains same. And at the exit point what is the pressure? So pressure is given, that is 1.5 bar. So this isentropic expansion process is taking place up to a pressure of 1.5 bar. So in the previous part, that is in the part 1, at the exit point we have taken here the point 2, but because of the throttling process takes place, we will take the next number, that is the point 3. So here we will say that the condition of steam at the exit point of the turbine will be at point 3. So when the isentropic process is taking place, so we have to show here the entropy will remain same. That is, here on the horizontal line entropy line is there. So we have to draw here straight vertical line. And it will intersect at the point of 1.5 bar, and here the new point will be 3 dash. Because the isentropic process is taking place. Now here the isentropic efficiency is there, that is 80%, and here the actual condition of steam is at point 3. So we have to show this enthalpy, that is the actual condition of steam, that is H3. So what is the relation in between this H3 dash and H3? Because here the isentropic efficiency is given, so we can say that this H1 dash minus H3 dash, H1 dash minus H3 dash multiplied by this 80%, that is 0.80 is equal to 80%, that means 80 by 100. So 0.80, which is equal to actual difference, that is H1 dash minus H3. So in this we can put the value of H1 dash and H3 dash, and we will find out the actual enthalpy, that is H3. Now again, here is the mixture of steam and water which is passed to the process plant. So here is the enthalpy H3. So after this steam is coming out from the process plant, it is converted into saturated water. So saturated water, we can say that enthalpy is HF3. So pressure will remain same, that is 1.5 bar. So I will say that here will be HF3. So from this steam table we can find out this value of HF3, because here the fluid is in the liquid phase, that is saturated water is there. So at 1.5 bar pressure we will find out the value of HF3. Now this saturated water is again pumped back to the boiler. After the throttling process, now we will select the point 1 dash. So here what is the condition, that is the pressure is given 7.5 bar and the enthalpy will remain same for the point 1. So point 1 that we have already selected. So here is the point 1 that we have selected, and the enthalpy that is also getting selected. Now we have to extend this point for the constant enthalpy. So this red line is the enthalpy line. So we have to extend this line for the constant enthalpy. That means in straight way we have to extend this line up to a pressure of 7.5 bar, because the throttling process is taking place up to a pressure of 7.5 bar. So if we observe this pressure, here is the pressure 4. Then there are two lines, and here is the pressure 10. That is, this value is 6 and then 8 and then 10. So in between 6 and 8 there is the pressure, that is 7.5 bar, that we have to select, and we will extend this line up to a pressure of 7.5 bar. So I will select here the different color line to understand this. So I will draw here one straight horizontal line. So this is the horizontal line that we have to extend. So if we select its sides, then this is the horizontal line. Now we will select the point, that is enthalpy for this H1 dash will be same, that is 2930, that is same as point 1. Now we will find out the point after isentropic expansion process is taking place. So for this isentropic expansion, entropy will remain same and final pressure is 1.5 bar. So if we observe here, here is the in between 1 and 2, there is the pressure line for 1.5 bar. So we have to extend this line up to this pressure of 1.5 bar in this vertical line, because the entropy remains constant. So this is the entropy on this horizontal line, and this remains constant. So we have to draw straight vertical line. Now how to measure this point? So this point will be 3 dash, because point 2 is already getting selected in the first part. So this is the second part, that is for throttling process. So after this point 1 dash, this point will be point 3 dash. So again we have to find out the enthalpy for this point. So we will draw here the horizontal line passing through this point. I will draw here the horizontal line. So what is the exact value? So if we observe the exact value, this first part is 400, that is 2500. Here is 2600, and after that exact value is H3 dash 2670 kilojoule per kilogram. Now we will find out the value of H3 because this is the value H3 dash for this isentropic expansion, but isentropic efficiency is given, that is 0.8. So we have formula, that is H1 dash minus H3 dash multiplied by 0.8, which is equal to H1 dash minus H3. So now H1 dash H3 dash are known and only one unknown value, that is H3, and H3 is equal to 2722 kilojoule per kilogram. Power developed by generator. So what is the power developed by generator? So here the pressure is reduced by 50% and the load is also reduced by the 50%. So here power developed is also reduced by the 50%. So we have to take power developed by generator, that is 500 divided by 2 kilowatt. So we have to take this power developed by generator. Now what is the relation in between the power developed by the turbine and power developed by the generator? So we have to multiply with this mechanical efficiency and generator efficiency to the power developed by the turbine, because after passing through this mechanical conversion and this generator, then only electrical power is getting developed. So we will write here, that is power developed by turbine multiplied by mechanical efficiency multiplied by generator efficiency is equal to power developed by generator, and which is equal to 500 by 2. So we will put the value, that is PT multiplied by 0.90 into 0.95, which is equal to 250. So PT is equal to 250 divided by 0.90 into 0.95. But how we can find out this power developed by the turbine? That is, it is nothing but the enthalpy difference in between this point 1 dash and 3 multiplied by the mass of steam supplied. Now the mass of steam supplied when the throttling process is taking place, we will use here the MS1, because in the first part we have taken MS without the throttling process. So we will take here the MS1. So PT is equal to MS1 H1 dash minus H3. So from the diagram we have to take this enthalpy difference. So this H1 dash is known, H3 is known, and PT we have to put this value. So MS1 is equal to 1.406 kilogram per second. Now we want the answer in kilogram per hour. That is, in 1 second this amount of steam is supplied. That is 1.406 kilogram. So in 1 hour, how much steam is supplied? So in 1 hour there are total 3600 seconds. So we will multiply here 3600. Then this is the answer, that is 1.406 into 3600 kilogram per hour. Now we will move to the next question, that is the heat supplied to the process plant. So again same formula is there, that is the amount of steam supplied multiplied by the enthalpy difference. Now enthalpy difference, if we observe the diagram, here is the enthalpy H3 and here is HF3. So HF3, that is at 1.5 bar. So from steam table at 1.5 bar the value is 467. So we will take the MS1, that is 5060.7, that is, this value is nothing but in kilogram per hour. So remember, this multiplication is 5060.7 multiplied by 2722 minus 467, which is equal to 11.41 into 10 raised to 6 kilojoule per hour. Now answer should be in megajoule per hour. So here we have to divide by 10 raised to 3. So we can say that 11.41 into 10 raised to 3 megajoule per hour is the answer.